For homework number 13, I've modified that assignment again. You'll remember that a couple months ago we had a pair of snow days where we didn't make it in for about a week, and we're still feeling the effects of that. As a result, I have eliminated the handout problem that I would normally have you do. And instead, you're just going to work two problems. This homework 13 is due next Tuesday. And I've given you a hint for those two problems because they don't explicitly say in the text which method you're supposed to use with what problem. And so in problem 15.2, I've let you know that you need to use the numerical integration method for that. And then problem 36 is the standard step method. So any questions about that? Due Tuesday. We're going to go over both of those approaches today. All right. We're going to skip this example so that we can go through those the standard step method and the numerical integration method a little bit more slowly. Are there any questions, by the way? Homework 13 is due on Tuesday. Okay, we're going to duplicate the same process of classifying the water surface profile in the first example we will work. So we're okay skipping through this, but when they ask you to classify the water surface profile, essentially they're wanting to know, does the slope make it mild or steep? And then which of those three zones does the water depth that's described fit into? So we'll go through that process in just a minute here. One of the applications for water surface profile and finding depths is at stream gauges. Now, in West Virginia, there are about maybe 100 places where river depth is measured, and that data is available from the internet. And if you think about the number of rivers and streams throughout the state, 100 is really just a minuscule number. There's just thousands and tens of thousands of creeks that are significant where there is water going underneath a bridge or water going through a culvert. So a lot of places where you wish you know what the depth is, but you don't have direct access to data like is shown here. This is sort of a cross-section of what a gauging station looks like. They have a wet well connected to the stream that's being measured. Water flows freely between the two, and then they've got some sort of an instrument, whether it's a pressure gauge or a float connected to a string. And just every so often they're measuring what the depth is. Even at those few 100 places in West Virginia where they are measuring the water depth, at the vast majority of them, all you can find out is what was the average daily flow. And so you don't know what the depth was in the morning, in the afternoon. On small streams, there can be huge variations in flow over the course of a day. And so really, we have limited data available at rivers to tell us where the water is at, especially when you consider that at some of the rivers, like on the Ohio River, where they do measure the depth, the stations can be 20, 30, even 50 miles apart. And so the methods that we're going to go over today are ways to approximate what is the depth of water at a location where you don't know it, starting with a location where you do know the depth. And so that known is going to be at a gauging station like this. And you're working upstream or downstream to try and determine what will be the depth. And you're trying to account for how are flow conditions different between the two places where you're interested. Here's a photo of a stream gauging station that ironically, you can't quite see it. It's a stream gauging station that was flooded out. So they couldn't even go down and access the instrumentation that was measuring the water level. And this is in Indiana when I was in grad school. So the first of the two methods we're going to talk about today is the numerical integration method. Most of the time, this method is used when you know a depth someplace and a distance upstream or downstream that you're interested in, and what you're trying to find is the other depth at that location further away from your gauging station. It doesn't have to be used that way, though. Sometimes, and in your homework, the way that they're using it is find the distance between 2 points of known depth. And I'll show you how you can apply the method for both questions. What it's doing is it's starting with the process equation for gradually varying flow. And remember that this just describes the changing water depth at a point. And so it's going to try to apply this method at a point between two distances. And when we use this method, we're going to have to do some intermediate calculations, including the Froude number at the midpoint between the two places that we're interested in. We're going to have to calculate the slope of the energy grade line, rearranging Manning's equation, and solve for S sub f at the midpoint between the two locations where we are interested in. And usually the length between the 2 points, there's an upper limit of between 30 and 150 meters. And if you solve for points that are further apart than that, it can introduce a lot of error. So if you want the most accurate estimate possible of what is the depth at the different locations or how far apart they are, what you do is you divide it up into lots of little pieces, and then you estimate it that way. So I'll have a diagram in just a minute that shows what I mean by dividing the two distances up into segments, or legs as they're called in the handout. Here's a summary of the steps that we go through. The text is the source of this notation system, and so if you don't quite follow the discussion that we're going to be going through, I'd encourage you to read through the text. Like I said, you're going to be calculating conditions at the midpoint. And so that if the water depth, just as an example, is decreasing, now let's say here would be location 2, here would be location 1, what we're going to do is estimate what's going on here at the midpoint. And so at the midpoint, we want to know this equation, f bar, comma, x, f of x and y bar. The bar here, the notation, that means at the midpoint. And so we're going to find the distance between the 2 points of interest. And so we'll find the distance from the known segment to the midpoint. We're also, y bar means the depth at the midpoint. So here would be y2. Here is y1, and so y bar is the depth at the midpoint. When you have subcritical flow, and you diagnose that by comparing yc versus y sub n, you look at the critical versus the normal depth, and that tells you whether subcritical flow or supercritical flow exists. And the equation's a little bit different depending on which you've got. If you've got subcritical flow, then you work upstream, meaning that you start here downstream at some known depth, and then you work upstream to try and find, what is the depth a known distance away, or for a known depth, how far apart are the two segments. So in the process, we're going to find all these parameters at the midpoint, including the distance, depth, cross-sectional area, wetted perimeter, hydraulic radius, slope of the energy grade line, velocity, and Froude number. And once we find those conditions at the midpoint, then it allows us to predict the unknown depth. Okay, so here's the example we're going to start with. And we're going to solve this to begin with in one step. We know that at a certain location, the water depth is 0.8 meters. You can see from the diagram here, water is flowing over the edge of a drop. And so if we went further upstream, eventually it was flowing at the normal depth. It was flowing along at the normal depth, but then the water level started going down because of this drop-off. And so we're in this section of gradually varying flow. And so we know that here, at this location, the depth is 0.8. And what we're going to try and find out is 50 meters upstream from that, what's the depth at 1? Okay? So we'll go through the process of starting with calculating the critical depth and normal depth. So we want to know y sub c and y sub n because that helps us to know whether the slope is mild or critical. We have to know that to know whether to use equation A or equation B. They're different depending on the flow conditions. So let's start with that. We'll begin by finding the critical depth. Now this is a rectangular channel. The width of the channel is 5 meters. Manning's roughness, 0.015. The slope is 0.001. And the flow rate is 10 cubic meters per second. Okay, so the critical depth, y sub c, we can find that for a rectangular channel. It's the flow per unit width squared divided by g to the 1/3 power. The flow per unit width is 2 meters squared per second. We square that, divided by 9.81 meters per second squared, and that's to the 1/3 power. So the critical depth is 0.742 meters. And we'll compare it to the normal depth, which we get from Manning's equation. For traditional units, that's Q is equal to area. I'm sorry, this is metric units, SI. 5/3 N times P to the 2/3 and slope to the 1/2 power. So we'll substitute in all of the known values and just solve for y. 10 cubic meters per second. The area is 5 times the normal depth. That's to the 5/3 power. The n value is 0.015. And the wetted perimeter is 5 plus 2 times the normal depth. And the slope is 0.001 to the 1/2 power. So we solve for the normal depth here and get that the normal depth is 1.124 meters. Okay, so let's do this comparison. We have the deepest of them is the normal depth. We've got the normal depth and then the given flow depth at location 2. And then we've got the critical depth, y sub c, okay? Because the normal depth was 1.124, the flow depth was 0.8, and then the critical depth was 0.742. The fact that the normal depth is greater than critical depth, that tells us it's mild. We have an M profile. And then the fact that the given flow depth at this location of interest is between normal and critical, that puts it in zone 2. So this is an M2 profile. And what M2 means is that it's getting shallower downstream and deeper upstream. So when we go through our calculations, what we're looking for is, we'll know there's a problem with our calculations if it gives us some shallower depth upstream. It should be a deeper depth upstream since this is an M2 profile. So we'll keep that in the back of our mind as we're doing the calculations, just to do sort of a reality check to make sure that it matches that behavior that we already know about. Any questions so far about how to find the critical depth, how to find the normal depth, or how to know what profile type it is? You can definitely expect that diagnosing the water surface profile will be on the final exam. No, it's when you've got a mild slope, but the flow depth is less than the critical depth, but then you'd have a hydraulic jump. So if you had temporarily supercritical condition, supercritical flow on a mild slope, that's what will support a hydraulic jump. Okay, so here's our location of interest. And we know that here it's an M2 profile and it's getting deeper upstream, and we want to know how deep is it 50 meters upstream. What I'm going to do is I'm going to start Excel, and I already have the kind of the layout that I like to use for these problems in Excel. You don't have to mimic this same layout. You can use whatever spreadsheet approach you like. But, oops, did I just close that? As a reminder, you know, I'm recording this lecture so that if you want to refer to it as you're working on the homework, then you don't have to feel like you furiously transcribe or take pictures of the screen, because that picture, so to speak, is already being taken for you. But remember that kind of the key to this process is we're going to find out what's going on at the midpoint. And we're starting off with a depth at 2 of 0.8, 50 meters upstream. What is the depth? We have to start with the guess. We'll begin with the guess. And so here at 2, it was 0.80. X is 50 meters. And so just as a guess, I mean, we have to start somewhere. I'll say maybe it's 0.85. And we'll go through iteration to try and check our guess and see how good it is and gradually improve. And as you might expect, we'll use Solver to automate that process. But I'm going to begin with a guess depth at Y1 of 0.85. And I chose that, you know, it's deeper. I wouldn't want to make it shallower. That wouldn't be a very good starting guess. All right. So what we have here is the flow conditions. It's a rectangular channel with the flow rate is 10 cubic meters per second. The width of the channel is 5 meters. Here's the slope of the channel, Manning's N, and the depth at the known location downstream. The distance between the 2 points, we're already given that that's 50 meters, and then I'm going to guess that upstream at 1 is 0.85. I could have started with another guess and I'd still get the right answer eventually. So here at the midpoint, how far is it from our known location to the midpoint? That's 25, so I'm just going to do this distance between the 2 points divided by 2, half the distance. What's the depth there at the midpoint? I'll just do the average of Y2 and Y1 for the depth at the midpoint. Okay, so equals Y1 plus Y2 divided by 2. Okay, so that's the average depth between the two. The cross-sectional area at 2 is going to be the width of the channel, because it's rectangular, times the depth at the midpoint. A wetted perimeter for a rectangular channel is the width of the channel plus 2 times the depth. So it is the width plus 2 times the depth at the midpoint. Hydraulic radius, it says here that it's the area divided by the wetted perimeter. So equals area divided by wetted perimeter. Now this is the first one that's maybe a little bit tricky in terms of, translating an equation into Excel. This is just Manning's equation solved for the slope of the energy grade line, and I want to do it at the midpoint. So here's my energy grade line up here above the water surface, and I want to know what's that slope at the midpoint. So I've got the equation written here, solved in terms of the slope of the energy grade line. So equals parentheses n times q divided by the area at the midpoint times the hydraulic radius at the midpoint to the power of 2/3. And then I just have to make sure I put in the appropriate number of parentheses. Looks like I've got them all there. Okay, so slope of the energy grade line. Velocity is the flow rate, Q. Oh, thanks. Yep, good catch. Very good. Squared. All right. Now we don't have to hunt for the error later. You keep on me, all right? All right. Q divided by the area at the midpoint. So that's the velocity at the midpoint. Now Froude number, here's the Froude number equation. I want Froude number squared. So I don't have to take the square root of the right side. It just so happens I want Froude number squared. So equals q squared times the top width, which is the same as the channel width, divided by G, 9.81, divided by area cubed. Sure, yeah. Okay. Now I'm going to use this equation to find the f of x bar y bar. So it is the channel slope, equals the channel slope minus the slope of the energy grade line at the midpoint, and then divide that by 1 minus the Froude number squared. And here I already have the Froude number squared. Okay, so now I've got that. And now it was subcritical flow, and so I'm using this equation. Remember that if it had been supercritical, I would have used equation B, and you work downstream. But here it's subcritical, so I'm using equation A and working upstream towards the unknown depth y1. So it's y1 is y2 minus that thing. So I'm going to use this to calculate y1. So it is the y2 that I started with, this known y2, and then minus, excuse me, minus this equation times the distance between 1 and 2. The total distance being 50 meters here. Okay? So my guess wasn't very good. I remember I initially guessed that the depth was 0.85. If I had guessed the correct depth at 1, then these two would match. So I'm going to have a difference thing here because it'll tell me if I'm getting close or not. So the difference between my guess and the computed depth at 1, I want this difference to be down to 0. Right? So I can do that either by just typing in a lot of values until it finally gets there, just a bunch of random values. You know, 0.9, does that get me closer? Yeah. 0.9 is a better guess. What about 1? It looks like now I've maybe overshot it. So, of course, the smart thing to do is to use goal seek or solver. And my objective is I want the difference between my guess and computed y1 That's the objective. We want it to be 0 because I don't want the difference to be big. And what it changes is this guess value here. And so we run it, and it found a solution. The depth at 1 is 0.944. 0.944. So it's not 0.85, it's 0.944. Okay, your homework, you can use the same spreadsheet, but it's asking something different in your homework problem. In your homework problem, imagine what if they had said, okay, we know that it's getting deeper upstream. At some point upstream, the depth is 1 meter. So how far is that between where the depth is 0.8 and where the depth is 1? Okay? And that's the style of your homework. And so how do you suppose you would use this approach where you have actually a known depth at 1 and 2? Well, in that case, the unknown is the distance. And so you're just going to keep playing around with various distances until your guess value and your computed value are the same. Okay? So it's not hard at all. You can just still use goal seek. The one thing that's a little bit tricky in the homework assignment, and I've tried to eliminate some of that confusion, is that if the points are too far apart, you can get error. And so you break it up into segments, and rather than going from, just as an example, rather than going from 8 to 1, a way to get a more accurate answer would be to say, well, let's go from 8 to 9, and then from 9 to 1. So if we did it in 2 steps, then each of these little segments are smaller. And so that then we'd want to know how far apart is it to go from 0.8 to 0.9, and then how far is it to go from 0.9 to 1. And so you're breaking it up into smaller pieces, and you get improved accuracy. And actually in the homework, they ask you to do it in 3 segments, and I've given you the depths to use in between. That's the numerical integration method. It's limited, though. The numerical integration method is limited to channels where the cross-sectional shape isn't changing. You can't use this approach if location 1 is wider than location 2 was. And you can't use this if it goes from rectangular to trapezoidal. And so this has a pretty narrow application. It's simple to use. It's simpler than the next approach that I'm going to show you, but it only works when you've got a prismatic channel that is constant in shape between the 2 points in question. The standard step method isn't limited to that. The standard step method is a little bit more robust. Now you're going to have to skip through a bunch of notes because I printed this at the beginning of the semester, and we're not doing the step-by-step method. So find the note that has the alarm on it, where it says standard step method. All right. So the methods, the step-by-step method and the numerical integration method, which we just talked about, is limited to where the cross-sectional shape isn't changing. The standard step method can be used when you've got a changing cross-section. And so the types of computer programs out there that automate this, they use the standard step method. Because out in the real world, rivers are changing width, and they are changing shape. And so the numerical model that's used by the Army Corps of Engineers and a lot of private contractors is called HEC-RAS. And in fact, this semester in senior design, the students in the hydraulics and hydrology group are using HEC-RAS. And behind that is this method that you can set up with a spreadsheet. You don't have to do it in like a computer model in a fancy graphical interface. You can just set it up in Excel, and that's what we'll do today. So let's take a look. This is the same diagram we looked at in a previous lecture where we saw that there are three different slopes. There was the slope of the channel bed, the slope of the water surface, and the slope of the energy grade line. And we saw that the depth was increasing, and so the velocity was changing. Now the difference here is we have some horizontal datum that we're measuring everything against. And what you can see is that we're going to be measuring what we call water surface. WS stands for water surface. And that is the measurement of from the datum to the channel, so that's the Z, and then from the channel to the water surface, and that's the Y. The reason why I put an alarm notification here is that location 1 and location 2 mean different things when you're doing the standard step method than they've meant before now. Like through the whole semester, I've always said, let's let the number 1 mean upstream and the number 2 will mean downstream. But in the standard step method, that's not what 1 and 2 means anymore. Here, 1 means the place where you know information, and 2 means where you don't know information, like where the depth is unknown. So it's not about upstream, downstream when you're working with the standard step method. Okay, so this equation here, this is saying that this is an energy comparison. It's saying at location 1, we've got the elevation from the datum to the water surface, so that's WS1, plus the energy grade line, the distance from the water surface to the energy grade line, so this is the velocity head, and then the head loss. The head loss term is on the left side of the equation here because the flow is going from 2 towards 1. We've got subcritical flow here, and so our known section is downstream. This is where we'll know the depth, and since we have subcritical flow, we'll work upstream and try and find out what is the depth some distance upstream where maybe the channel is changing shape, or maybe the width of the channel is increasing or decreasing. There's just some sort of a change in channel geometry that's influencing what the new depth will be. So the take-home method, the take-home lesson here is the new convention, the new assigning of variable convention. 1 is where you know something, and 2 is where you don't. And we're going to do a total energy balance. We're not just going to balance specific energy here, but we're going to account for the head losses between 2 points that's due to the resistance of the channel. So this looks like an explosion, right, on the screen here. This explosion is a summary of the method that you go through when you're doing the standard step method. So again, we're going to do it with a spreadsheet. And as I go through the spreadsheet, this is what I'm trying to follow, this approach. Just like we did in the numerical method, the numerical integration method, at first, we don't know what the unknown depth is, and so we have to guess. We'll start with a guess. And so the first thing that we'll do is we'll just make a guess for how far is it from the datum to the water surface at location 2. And sometimes you can get like a first stab at what that depth should be by water surface profile classification. Remember that when I did my first guess here, I said 0.85 because I knew it should be deeper upstream. It's the same kind of thing where don't pick a depth that's less than if you know it should be getting deeper upstream, because if your guess is bad enough on this approach, you'll never get a right answer. Some methods are more forgiving than others on how close your initial guess has to be. And this method, actually, your initial guess doesn't have to be super close, but it can't be ridiculous. All right. We're going to define a couple of terms here. We're going to call the observed head loss, HL observed. That's going to be the difference in the energy at 1 and 2. And energy is the sum of the water surface plus the velocity head. where WS is both the depth and the delta Z. Okay, so that's head loss observed. And then we're going to compare the observed head loss to the calculated head loss, where the calculated head loss takes into account the slope of the energy grade line at the midpoint. So this is the same calculation that we did in the last example, where we're using Manning's equation to find out what's happening at the middle between the known section and the unknown section. So here's Manning's equation solved for S sub f. But then we're also going to account for losses between the two sections, because remember, this method can be used when the channel is expanding or contracting. And in a previous lecture, we talked about how if a channel gets narrower or wider, or if it changes geometry, there's going to be energy losses because of that. You know, it's water's flowing along and it has to reestablish flow. And so there's going to be some turbulence as it does that. And the C value tries to account for the energy that's lost during this transition. And so there's two terms to the calculated head loss. It's partly about the energy loss due to friction between the 2 points. And then this second term is analogous to local losses. You know, it's losses because of a change in channel shape. So we'll compare those two, and if they're not exactly the same, then we have to update our guess of what is the depth of the water at location 2. So this WS2 calculated is an update based on the difference between the observed and the calculated head loss. And so we'll go through this process of comparing the updated the updated depth to the original depth, and we know that we've achieved convergence when the two match. Okay, so this is the example that we're going to use to try and apply the standard step method. Section 1 is where we know the flow conditions. And so at section 1, it's a trapezoid. You can see that the known depth is 5 feet, but then 1,000 feet upstream of that is a rectangular channel, and we're not sure what the depth is upstream of that. Okay, so the starting point for this, just like the last example, is to calculate the normal depth, the critical depth, and diagnose the water surface profile so that we can guide our first guess of what the depth at the unknown section should be. So the distance between the 2 points is 1,000 feet. The delta Z, you can see that in the section on the right, section 2, it says invert is 7 feet. That's just the distance from our datum to the bottom of the channel. And the invert downstream at section 1 was 5 feet. So the delta Z is 2 feet. That's the elevation difference between the bottom of the two sections. And so the slope of the channel is 2 divided by 1,000. So that's 0.002. That's the slope of the channel. Okay, we want to find the normal depth. And that's going to be Q is equal to 1.49. The 1.49 is the conversion factor we use when we're working with the British gravitational units. And then we have area to the 5/3 and perimeter to the 2/3, and slope to the 1/2. If it's a trapezoid, like we have, where it is 25 feet at the bottom, and the flow depth is the normal depth. That's what we're trying to find, is what's the normal depth at this location where conditions are known. Because the side slopes is 2 to 1, where it's, for every 1 unit of depth you have 2 on the side, then that means over here it's 2y sub n, and over here it's 2y sub n. So the area is going to be 25 times y sub n plus 2yn squared. That's the area of the trapezoid. And the wetted perimeter will be 25 plus 4.472 y sub n. And what I did there is, here it's the square root of y plus y squared plus 2y squared. So that is equal to 4.472 y sub n. Well, that's both sides. So that's each side is going to be 4.472 divided by 2. Okay, so if you want to consult table 10.1, then you'd get the same things ultimately. So if we substitute that into Manning's equation, the flow rate is 1,000 cubic feet per second. .49, the cross-sectional area, 25y plus 2y squared, and that's to the 5/3 power. And the n value is 0.05. The n value is given on the slide there. And then we've got the wetted perimeter, 25 plus 4.472 y, that's to the 2/3 power. And then finally we have the slope, 0.002 to the 1/2 power. So we can put that into a solver and find that the normal depth, y sub n, is equal to 6.848 feet. That gives us the normal depth. We also have to know the critical depth in order to classify the water surface profile at this location where we know what the flow depth is. So critical depth we can find by solving the Froude number. We know that the Froude number squared is equal to q squared times the top width g a cubed. Now the top width of a trapezoid is going to be, t is going to be 25 feet plus 4 times whatever the flow depth is. So 4y. And what we're trying to find is, when y equals the critical depth. Okay, so when it's flowing at the critical depth, Froude number squared is 1. The flow rate is 1,000 cubic feet per second squared. The top width will be 25 plus 4yc. G is 32.2 feet per second squared. And then the cross-sectional area for critical conditions is 25 times y sub c plus 2 times YC squared, and then the cross-sectional area is cubed. So again, we can use solver to find out that the critical depth Y sub C is 3.346 feet. Okay. No, because the square root of 1 is 1. So we need to classify the water surface profile at section 1. So at 1, the flow depth is 5 feet. And so, is this an S or an M? Is it steep slope or mild slope? Why is it mild? Y sub n is greater than YC, so it's a mild slope. That's right. Are we in zone 1, 2, or 3? It's in zone 2. Since Y sub n is greater than Y, which is greater than YC, zone 2. And so this is an M2 profile. And what we know about an M2 profile is the water is getting deeper upstream. And so when we make a guess of the flow depth, we'll keep that in mind, that the water is getting deeper upstream. So any questions so far? Just starting some of the basic calculations to begin with. All right. Here's where we switch to the spreadsheet. Okay, I've pasted in all of these equations just so that I have them handy. Here's the form of what we're going to be doing. The known section is location 1, which for our problem is downstream. The unknown section are all of these things with the subscript of 2. That's the upstream section. Okay, so what we know at 1 is that the depth of flow, you can see right here from the drawing, is 5 feet. Okay, the area, we calculated earlier that the area is 25 times y plus 2y squared. Okay, so I'll type in that formula. It's equal to 25 times y plus 2 times y, which is A30 squared, 175. Okay, the velocity at location 1 is q divided by area. The wetted perimeter is going to be the formula that we had over here, 25 plus 4.472 times y. So we've got the wetted perimeter. Hydraulic radius is area divided by wetted perimeter. E1. Okay, the first time we have to think maybe. E1 is talking about the sum of the z, the depth, and the velocity head. So at location 1, you can see that from the datum to the invert is 5. So 5 plus the water depth, which is also 5, plus the velocity head. So I can say v squared divided by 2 times g, 32.2. Okay, so that's E1. And now slope of the energy grade line at 1. I'm going to use Manning's equation for the slope of the energy grade line. Let me drag it down so I can see it as I do my typing it in. Equals N times Q divided by 1.49 times the area times the hydraulic radius to the 2/3 power. And then square it. I won't forget the square this time. Uh-oh, what'd I do? Extra parentheses somewhere? Yeah. Yeah, it's the Z is, it's right here. It's the elevation from the datum to the invert, but I think I've typed something in wrong here. Oh, yeah, okay. Thank you. Good. Now, this isn't changing, so I can just drag all this down through lots of iterations, and I'm going to need to refer to that data over and over again. Uh-oh, it's counting. So it's 5, 5, 5. Okay. Y1 isn't changing. Oh, boy. Which one was it? Where was I referring up into there? The velocity? All right, yeah, thank you. I'll anchor that. All right. Getting closer, still need to anchor any reference up there to Q and N. All right. F4. All right, so here's the flow conditions at 1 where stuff is known. That doesn't have to iterate. Here at 2 is where things do need to iterate. Now, I know it's deeper upstream at 2, so I'm going to say, well, 5.1 just to begin with. That'll be my first guess of what the depth is. Water surface, the definition of water surface is it's Z plus the depth. And so the Z is 7 feet, so equals Z2, 7 feet. I'm going to anchor that. Plus the depth at 2. So that's what we're calling water surface. The area at 2, for a rectangle, that's easy. It's just going to be the width of the channel, which is 25, times the depth. The velocity is Q divided by area. Q anchored divided by area. Wetted perimeter is the width of the channel, which is 25, plus 2 times the depth. 2 times the depth. Okay, hydraulic radius is area divided by wetted perimeter. Okay, E2. Remember, energy, what we define as energy is it's the elevation above the datum of the invert plus the water depth plus the velocity head. Okay, so here for E2 I'm going to have 3 components. It's going to be the water depth, the Z, and the velocity head. WS2 is Z2 plus Y2, so I might as well just use that. So WS2, which was Z2 plus Y2. Now the velocity head, so that is V squared divided by 2G. Okay, so that's the energy that's available at 2 under this guess. Slope of the energy grade line, I have to use Manning's equation again to find the slope of the energy grade line at location 2, so equals N anchored times Q. Of course, the nice thing is once we type the equation in one time, we don't have to do it again for our future iterations. And so the first row is always a little more tedious than the other ones. The area at 2 times the hydraulic radius at 2 to the 2/3 power. And then all of that is squared. Okay, so that's the slope of the energy grade line at 2. Now, head loss observed. If we go up here into the formulas, tells us the observed head loss is just the difference in E2 and E1. So equals E2 minus E1. What we're hoping for is that the observed head loss and the calculated head loss will be exactly the same. If they are, then that means we don't have to do any more iterations. They won't be on this first guess, though, because I just pulled 5.1 out of thin air. So it would be pretty unusual to have that first guess be perfectly right. S sub f bar, that is talking about the average slope of the energy grade line. And so I'm going to just simply have this plus that divided by 2 for the average slope of the energy grade line. And so now the calculated head loss is the slope of the average energy grade line times L, the distance between the two. And L here is 1,000 feet, since they're 1,000 feet apart. And then it's taking into account the local losses due to the transition. So the C value, the transition coefficient that's given, is 0.3, and we're going to have the difference in the velocity heads too. So this one, I'm going to drag it down so we can refer to the equation as we're typing it in. Done with that. All right. Okay, so that calculated head loss is this average slope of the energy grade line times L, which is 1,000 feet. I need to anchor that. Plus the C value, anchor that as well. And now times the absolute value of the velocity head at 2. So that is v squared divided by 2 divided by 32.2 minus, I'm going to put in an extra set of parentheses just to be sure. Oh man, thank you. That would have really messed things up. All right, so now I need to have the velocity head at 1. So start off with the velocity at 1, this squared divided by 2 divided by 32.2. It did the same thing. Some people, you can't learn sometimes. All right. Okay, so the calculated head loss does not match the observed head loss. So we know that we didn't get it right miraculously on our first iteration. So the way to correct our value is to calculate a new updated version of what the water surface at 2 should be. So the update is going to be the average of the calculated and the previous. And so here is what we're going to use for the calculated water surface. Let me move that out of the way. Okay. So WS2 calculated is water surface at 1, which is the elevation above the datum plus the flow depth plus the velocity head. I should have just made a column that was WS1. In fact, I'm going to do that now, just because it'll save me time in the long run. So this is WS1 in feet. So it is Z1 plus Y1 plus the velocity head plus, check this out, did it. Yes, yes. If it's not one thing, it's the other. All right. Okay, so that's the water surface at 1. Yeah, all right. Well, I'll lock the velocity and I'll lock the z, which is what I should have locked in the first time. All right. Yeah. Okay, so that's WS1. With all these empty rows below it, it seems like we're going to be here forever, but we're not. Once we get this working, then it all falls together pretty easily. Okay, so again, what we're trying to do is this equation. So the calculated water surface is the water surface at 1, which we can get from over here now that we made it, plus the velocity head at 1. This shouldn't have had the velocity head in it to begin with, but see, that's actually E1. It's the same thing. Let's just delete the whole thing there. Went to all that effort. Okay, basically, WS1 plus the velocity head at 1 is E1. So I'll save myself the trouble of just doing the E1 plus the calculated head loss minus the velocity head at 2. Okay, so minus V squared divided by 2 times 32.2. Okay, so that's the calculated, and now the updated is based on this calculated water surface. So the update will be the one we just calculated plus the previous version from here, and I'm going to want to average this, so I'll put in the parentheses divided by 2. Okay. So this is an update, and the percent difference I'm going to use is just an indicator of how close it is to convergence, and the comparison that I'm going to have there is the comparison of the calculated and the updated water surface, because when I'm finally converged, the two will be the same. So this minus that divided by that times 100. So I'm about 22% off right now. Okay, so the next thing is, what should we use as our updated guess of the flow depth? Well, the updated guess of the flow depth is going to be based on this new updated water surface, and so it's going to be, we're going to use Y2. This water surface is going to be that updated value. And so what is Y2? It is the water surface minus the elevation, the Z2. So that gives me what I should use as my new depth, and everything else just drags, including this percent difference. Okay, we have a big improvement. Now there's a lot less error there between the calculated and the updated. And so 8.6 is a much better guess for how deep the water is than 5.1 was. Okay, so the same thing. I think at this point I should just be able to drag everything down and it'll automatically converge. Okay, let's see, it was here. Yeah, you're right. All right, now let's see if that works. Yep. All right, so it's going down towards 0. The guess and the calculated are the same. My depths aren't really changing. I could drag it a few more rows just to make sure that it stabilizes. And it has 8.05. So that's the actual depth at 2. That's how deep the water is if it's getting narrower. And you kind of would expect that, right? Two things are happening simultaneously. We've got the gradually varying flow that's because water is approaching a drop-off, but then at the same time as that, the side slopes that were fanned out are now, the channel's effectively getting narrower because you're losing the side flow area. So those are two things that are driving the depth at location 2 upstream where we didn't know it to get higher. So that's how to do the standard step method. And in the homework assignment you've got one problem of each. You've got one numerical method and one standard step method problem. So I will turn you loose on those. That's all the time we've got for today. I don't think we'd have time to go through the second standard step method problem, so we won't even start on it. Just remember that for next Tuesday, problem 2 and problem 36 will be collected on Tuesday. If I can just make one announcement about the project, and this is pretty important. I think some people I've already corrected on this misconception, and some of you haven't got to the crossroads yet to make the error. Let's talk about the tanks. So I give you pricing data for, I think, 3 different tank sizes, right? One of them is 5,000 cubic meters. Does anybody remember what the 3 tank sizes were? It was 5,000 cubic meters. 20,000? All right, 20,000. And then, anybody have the handout for the project with them?
Yeah, I got somewhere in between those probably.
I think it was actually lower than 2,000. All right, 2,000. And then 16. All right. So you're not just supposed to pick the one that's closest to your required volume. What you're supposed to do is you're supposed to build the volume that is required, and then you estimate the price by interpolation. And so interpolation is you'd put the volume here, and you'd put the price here, and you've got 3 data points. You've got the 2,000, you've got the 5,000, and then you've got the 20,000. And so just linearly interpolate so that if you need a 4,000 cubic meter tank, you would just estimate the price of that between the cost of the 2,000 and the 5,000 cubic meter tank, and so on. So that's one of the points I wanted to say, is that some of you didn't put the cost of your tank in the submission that you already did, and that's fine. I didn't ask for the cost yet, but for those of you who did, some people weren't interpolating the price, and you need to do that. One other thing is that the submission for the final report is going to be electronic. So you've done electronic submissions for the maps, for the spreadsheets, and so your final report will be electronic submission as well. On Tuesday of next week, I'm going to show you how to put multiple PDF files together in just one file, because that's what I'd like you to do, is put your maps, your spreadsheet, put everything into one continuous PDF. And if you don't already know how to do that using Adobe Acrobat, it's a good skill to have. So we'll talk about the project submission a little bit more on Tuesday. And so I'll see you then.